All right, so let's move on now to talk about reactivity. So, as we've seen before, the carbonyl group of ketones and aldehydes primarily reacts as an electrophile, which again I'll symbolize using the symbol E+. So, why is a compound like acetone electrophilic? Well, just to sort of rehash what we've covered before, there's two reasons that we can look at here. One is induction, so there's a strong inductive effect between the carbon and the oxygen, which leaves a partial positive charge on the carbonyl carbon. The other reason we looked at was resonance, because we can push these electrons up towards the carbonyl oxygen. This generates a resonance form that has a carbocation at that carbon and would mean that in the hybrid there would be a partial positive charge there as well. So because of these two reasons, induction and resonance, carbonyl groups are actually pretty good electrophiles. Now, back in Organic 1, we sort of just told you that you had to know that aldehydes were better electrophiles than ketones, but now we can actually explain why. It's a combination of both steric and electronic effects. So if we look sort of generically at an aldehyde versus a ketone, we can see that there is a steric effect, right? The aldehyde is considerably less hindered than the ketone, even if you have two small groups like methyls. That makes the aldehyde a significantly better electrophile. It will react much faster with nucleophiles. There's also an electronic reason. After the electrophilic aromatic substitution chapter, we've pretty much well established that alkyl groups are electron donating. If we place more electron donating groups around a carbon which has a partial positive charge, we will stabilize that charge, which will make it less electrophilic. So for both of these reasons, we tend to see reactions much faster with aldehydes than we do with ketones. So in terms of mechanisms of reactions, there's a couple things that we have to know. The first is we have to be very, very careful about our acid-base chemistry. And the second is that most of these reactions are, in one way or another, reversible. So we'll frequently see equilibrium effects. Now, I want you to have a mantra here when we're going through mechanisms. The first part of this mantra is that if I am drawing a mechanism for a process which is catalyzed by an acid, I must never draw an intermediate which is a strong base. So that means things like hydroxide, alkoxides, and the NH2- ion are completely off limits when there's an acid involved. Chloride and bromide or other species which are weak bases are actually okay. If I am drawing a mechanism for a base catalyzed process, I must never draw an intermediate which is a strong acid. So that means if we have a reaction which involves a base, things like H3O+, oxonium ions, HCl are completely off the table, whereas weak acids like water, alcohols, species like that are just fine. So let's see how we can apply this with one of the parent mechanisms of the reaction of ketones and aldehydes, the spontaneous hydration of the carbonyl group. All right, so what I'm going to do here is I'm going to say I'm dropping acetaldehyde in water. If I do so, I'm going to see the formation of something that's called an aldehyde hydrate. So here the aldehyde is said to have hydrated by picking up an equivalent of water. We've made this sort of weird looking geminal diol. How does this actually happen? Well, first thing is that there's an equilibrium to this process, and in general, the keto form, the carbonyl group, is actually favored over the diol because the carbonyl form is actually considerably more stable. We'll talk a little bit more about this equilibrium later. This process happens spontaneously because it's catalyzed by both acids and bases. Even trace amounts of acidic or basic even traces of acidic or basic species that are present in water will cause this reaction to happen on its own. So how does this actually happen? Well, imagine if we have a trace amount of some base, here B-, which is dissolved in water. This base can deprotonate the water to generate hydroxide. Now, why this matters is that hydroxide is a pretty good nucleophile and can therefore add as a nucleophile to the carbonyl group of our aldehyde. This generates another basic intermediate, which can pick up a proton from the conjugate acid of our base, forming our diol and regenerating our catalyst. So usually in this reaction, hydroxide is the species that's going to be acting as a base anyway. Here, though, I've shown it as a generic form, which we'll use frequently throughout the rest of the course. How would this be different if we had an acid? Well, if we have an acid, the first step is clearly going to be protonation of something, and the thing that's going to get protonated is the carbonyl group of our aldehyde. That makes this thing much, much better as a leaving group. It's now a very, very good electrophile, and so this very good electrophile can react with even weak nucleophiles like water. So here we get an oxonium ion, a strong acid as our intermediate, which can then be deprotonated by something. Again, I've shown just a generic conjugate base of our acid here. In reality, this is probably water that removes this proton. And what this does is it regenerates our catalytic acid and also gives us our diol. So take-home messages here. If we have a process catalyzed by a base, the quote-unquote point of the base is to make something a better nucleophile or to force out a bad leaving group. We'll see some of this later. If we have an acid, the point of the acid is to make something either a better electrophile or a superior leaving group. So the extent of this reaction, the actual equilibrium constant, can be a direct measurement of the strength of one of these things as an electrophile. So let's say I had these four compounds here and I wanted to know for sure experimentally which one of these things would be the best electrophile. Well, what I would do is I could measure the equilibrium constant of the hydration. One way of doing this is actually by using integration in the NMR. Heads up, this may appear on a quiz in your future. So the hydration constant of acetaldehyde is actually 2000, meaning that the hydrate form is favored a little bit over the carbonyl form. All right, that's pretty cool. Pivaldehyde, which we would expect to be a significantly worse electrophile due to that bulky terp-butyl group, is significantly worse as an electrophile. Its hydration constant is only 0.25. The aldehyde is favored. Acetone, a ketone, is even worse, 0.002. So what do you think at this point for benzaldehyde? Where's benzaldehyde going to fall on this spectrum? So think about this for a minute, and then come back and start the video again. We'll talk about it. All right, if you guessed that benzaldehyde would actually be a comparatively weak electrophile, you're correct. The reason why is that that carbonyl carbon is now conjugated with the aromatic ring, which makes it much more stable compared to something like acetaldehyde. Okay, let's practice this a little more. How about these two compounds here? Here we have chloroacetaldehyde versus trichloroacetaldehyde. Which one of these two compounds will be a better electrophile, and what can we guess about their hydration constants? Take a minute and work through this, then start the video back up again and we'll discuss it. All right, so here's the hydration constants. Chloroacetaldehyde has a hydration constant of 40. It's a much better electrophile than something like pivaldehyde. Now the reason why there is that we're going to have some inductive effects that will make that thing a pretty good electrophile. So if we add three chlorines on there, the hydration equilibrium constant jumps to 32,000. So all three of those chlorines really destabilize the positive charge on that carbon, which makes it a very, very good electrophile. In fact, this compound here, so the general principle being here that induction will destabilize the positive charge. The less stable that positive charge is, the better it is as an electrophile. This compound here is actually called chloral hydrate. In water, it precipitates out as a stable crystalline solid. This compound was once used as a sedative, called colloquially knockout drops. You've probably seen this featured in movies, if not necessarily by name. One movie where this plays a prominent role is the old James Bond movie From Russia with Love. I believe that it's also used in The Living Daylights, but don't take my word for that. You might want to look that one up.